Howdy. I wanted to show an example of using Riemann sums to compute exact area. And just to remind you of the things that we've talked about so far, what we said in class is that assuming that this limit converges, that the area of a region that is represented as the integral from a to b of f of x dx can be found by taking the limit as the mesh size goes to 0 of the sum from I equals 1 to n of f of ci times delta x sub I. And the only difficulty that we have with this is setting up our sum and then evaluating the limit. So we're going to break up the process into two parts here. First of all, we're going to talk about setting up the sum. And I'm going to continue with the example that we were looking at in class. So here's our problem. Find the area of the region bounded by y equals 2x, the vertical line x equals 1, the vertical line x equals 4, and the x-axis. Just to see what we're talking about, here's y equals 2x, no particular scale implied, and the region that we're looking at is this region R right here. So we can represent that area as a definite integral, the integral from 1 to 4 of 2x dx. So that's all well and good, and now how do we actually compute it? To do that, first of all, we're going to set up the Riemann sum. And in setting up the Riemann sum, we need to choose the delta x, really a partitioning scheme. And the easiest partitioning scheme is to make all of our delta x's be the same way. This is not the only partitioning scheme that we can use, and it's not always the best, but for a large majority of functions, it's going to be our best choice. And so we've found a delta x, and now the x sub I have to be computed based on that delta x. Since my delta x is an even-sized partitioning scheme, therefore the x sub I are going to be equal to the initial x value, that is 1, plus I times delta x. These two formulas here are what we might call an equally spaced or equal width partition. And you're going to see me use these a whole lot because this is usually the best way to go. So in our particular case, the delta x is equal to 3 over n, and then the x sub I are going to be the initial x1 plus I times 3 over n. Okay, that's our partition scheme. It's all set up. Now we're going to choose the c sub I, and we have lots of different possible choices: left, right, midpoint, upper, lower, other. But my favorite, and the one you'll see me use much of the time, is a right sum, where we let ci simply be equal to x sub I. And I think it's worth it at this moment to consider exactly what f of c sub I would then be. because c sub I being x sub I is 1 plus 3, 1 plus I times 3 over n. And since f of x is equal to 2x, therefore f of c sub I is 2 times 1 plus I times 3 over n, which simplifies to 2 plus 6I over n. This now allows us to set up the sum that our integral is going to be equal to the limit as, now if we want the mesh size to go to 0, here I'm writing my Riemann sum form, and the easiest way, or the way to do that here, is to let n go to infinity. So notice that this shift takes place because as n goes to infinity, then my delta x, remember that delta x is equal to 3 over n, so the limit as n goes to infinity of delta x then would be equal to 0. So that's how we let the mesh size go to 0. We're going to let n go to infinity, the number of rectangles. And that's when we get the sum from I equals 1 to n of f of x, f of c sub I times delta x sub I. Clean that up a little bit, and our first job is done. Our first job was to simply set up the Riemann sum, and we have accomplished that. Notice that we had to distribute our 3 over into both terms. Okay? Now, the next question is how to evaluate this sum. So, let me copy this sum and take it over to the next page. There we go. And I want to talk about evaluating sums a little bit. In general, evaluating sums can be hard, so we're not going to do a general theory on the evaluation of sums. But I do want to give a few facts about sums that are going to be useful for us. All of these are fairly easy to see if you simply take the sum and imagine adding up all the terms. And first is that the sum from I equals 1 to n of ai plus bi is exactly the same as the sum from I equals 1 to n of ai plus the sum from I equals 1 to bi. This is the same thing that we do when we add up, for example, a bunch of pennies and dimes, and we wish to add all those together. We would first collect all the pennies, then we would collect all the dimes and add them separately and combine the totals. Likewise, if I add up a constant times a sub I, that's the same as that constant times the sum of a sub I. And although this looks like a constant multiple rule, and you could call it that, it really is just the distributive property. And then finally, we can actually evaluate several simple sums. First of all, if I add up a constant, think about what this means. This means taking k and adding it to itself n times. And so the result is simply k times n. So you can think of this as a constant rule for sums. Likewise, if I add up I, that is, I add all of the numbers from 1 up to n, then what I get is the famous triangle curve, n times n plus 1 all over 2. There are a couple of other sum formulas that are sometimes useful, and I reproduce them in your homework. We're not going to prove them at this time, but you can make use of them as you see fit. In a discrete math class, you prove them using induction, everybody's favorite. So these are several sum formulas that are very useful to us when we are doing Riemann sums, particularly polynomials. And I want you to keep your eye on this one and on this one as we use them to evaluate our Riemann sum. We've set up our sum. We're now going to evaluate it by applying these limit facts over to the right there. First of all, we're going to take and split up our sum like so. Second of all, we're going to recognize constants. Now this is slightly tricky because we've got two different things going on here. We have n, the number of rectangles that is going to infinity, but within the sum we have this index variable I. When I talk about a constant inside the sum, I'm talking about anything that is not a function of I. And that would include all my n's. All my n's here are constants. So I can, in the first sum, I can immediately apply the constant rule where k is equal to 6 over n. And I can write the sum from I equals 1 to n of 6 over n as 6 over n times n. And that's applying my constant rule. With the second one, this factor of 18 over n squared is a constant with respect to I. So that when I factor it out, I get simply 18 over n squared times I. Cleaning all this up a little bit, my first one gives me 6. My second one is going to give me 18 over n squared now times the sum from I equals 1 to n of I. That is the triangle limit, n times n plus 1 over 2. Well, this is actually pretty convenient because at this point I've gotten to a limit that I know how to evaluate pretty well. That's 6 plus, now we have 18 over 2 would be 9. 9 times n plus 1 would be n squared plus n all over n squared. And it's pretty clear to see, using n models, that this limit is going to go to 1. So that when the dust settles, I get 6 plus 9, which is 15. And this is an exact value of the area of the curve, of the region under the curve. So just to summarize everything that we've done, we began with a region, we represented its area as a definite integral, and then we evaluated that definite integral by writing it as the limit of a Riemann sum. First with a partition, then with a choice of C, then we set up that sum, and we employ the basic trick that the mesh size will go to 0 if we let the number of rectangles go to infinity. That worked because our delta x was 3 over n, so that as n goes to infinity, delta x goes to 0. Having set up our sum with the limit as n goes to infinity, we evaluated that sum by employing the facts about sums and then taking the limit. And that's how the homework is going to go. I hope you appreciate two things. First of all, that it is possible to compute areas in this way. And second of all, it is a little bit tedious to compute areas in this way. So we are hoping for better tools in the near future that will allow us to find these definite integrals without having to resort to Riemann sums.